Anyway, we've got, I think right now the time is right for a program like this for a couple of reasons. Now, we've all heard the discussions of Moore's Law is coming to an end, or it's ended, or it's about to end. But we're not getting the growth. The speed up in the processors is not happening like it's happened in the past. There's this tremendous resurgence in AI. You know, a couple of years back, if you mentioned the word AI, people would look at you like you were crazy. That's something we did back in the 80s. But there's a tremendous interest in AI, and I think there's a tremendous potential and a tremendous future there. And I think if there's a community that can leverage that, it would be this community. You know, what community is better suited to sort of take the next step in AI than this group? And lastly, I think there's been a worldwide investment in this area. We had Ronald Test Lab organized a wonderful memoristive center. There's some very interesting work going on in Europe, a very, very good investment. We had Stan Williams here a couple of years ago talking about some of the very interesting ideas and interesting things happening in China. So I think now is a great time for us to invest in this area and go forward with it. But I think we need a bit of a paradigm shift. I think in the past couple of years, we've been focused on doing feasibility ideas. You know, can I take the existing chip? Can I put a deep learning network on it? Can I train it against MNIST? And can I show that it works? And we've all done this, and I think that's a very valid, very good thing to do. But I think we're at a point now of saying, but what's next? We've shown the feasibility of it. What's next? How do we start making this a little more interesting? You know, I kind of think we need to go native. We need to start thinking about native learning algorithms, and I think we need to start thinking about native data sets that we can use and work against. And I think we need a broader program. We need to work together in better, more interesting ways. So I've been, like Katie mentioned, I started this group many years ago, more than I want to admit. And we've done a lot of work in these areas of looking at large, complex data and trying to figure out how to do something with it, how to make sense of it. And a lot of the work that we've done has really been driven by the computers. You know, we started off with networks of computers. How do you move data between the computers faster? How do you do that? Then we get to clusters, and it's a little easier to move data. Then we get to GPUs. I remember doing work before CUDA was available, and trying to program on a GPU without CUDA, and that's a trick. Then high-performance computing, and then we spent a fair amount of time looking at these hybrids, where you've got a very large computer, you've got a GPU accelerator, and there's some very interesting things you can do. All that then tends to drive the algorithms that you can use. So we're now at this point where we've got neuromorphic chips. You know, if you couldn't make it to the Intel session was really, really good. Very interesting architecture, and I think a great step forward for the community. But we're starting to look at these things and starting to say, what is it that you can do? What is it that you can accomplish, and how can you move forward with this? As Katie mentioned, we've got, you know, Oak Ridge is interesting for a couple of reasons. One, we've got these very fast computers, very big computers. That's, you know, this is kind of what we do. And secondly is for the learning algorithms. We've spent a lot of time, we've done a lot of novel and clever and creative things in this space. And it's a sort of a unique place. We've got the combination of these two things together. Now, what we do classically is we look at scientific data. And so if you look at, you know, a large scientific experiment, this is an electron microscope, but it could be a spallation neutron source, it could be a 3D additive manufacturing printer, or a number of things. Out of this comes these images. Then you have an expert that reads the images, and they come out with this output. And so this is the way science has been done for years. It's a pretty traditional approach. The challenge is these are being produced at a much, much higher rate than these people can analyze. There aren't enough experts. You know, 90-some% of the data never gets analyzed, never gets viewed. And so the idea is to say, well, how do you fix that? You know, can you use computing to fix that? And so we've spent a fair amount of time saying we've got this big Summit supercomputer that's, you know, fastest in the world. We do a lot of work in this deep learning area, and saying, can we find a way of taking this and automatically characterizing it into this? And so we actually did this. And so we ran it on all the available nodes of Summit. We got this good result. The scientists say, this is something that we can't do right now. This is a new capability. And so we're pretty excited about this. And so this basically says we're kind of getting rid of the expert. We're sort of replacing the expert now with computationally. And then the next step is, and this is an area that I've pushed, that we've all sort of pushed to an extent, is to say, all right, now can I take this model that I've built, can I put it on a neuromorphic chip and start this sort of loop? Can I take my electron microscope, can I show a beam, can I analyze the result, figure out where to drive it next, and start driving atoms and start building materials? You could even think of start building machines or little tiny devices out of atoms. And this is an interesting idea, but I'm a little worried about it because I kind of go, this is sort of a pretty narrow niche to put a neuromorphic device. I kind of go, well, what if you could put an ASIC, or what if you could put a GPU in there that's got similar characteristics? And so I think it's, I kind of think there may need to be a broader view. So where we're kind of looking is to go, all right, I've got my deep learning, which works really well on imagery, and it's hard to say you're going to find something that does better than convolutional neural nets and GPUs. Maybe, but for imagery, that's a really strong combination. Well, there are a bunch of signals that come out of this big device, and to say, can we start looking at neuromorphic as a way of saying, can we start understanding some of the signals coming out? Can we look at some of the images? Can we look at some of the signals? When the beam goes in and starts moving the atoms, can we start understanding what that is and start modeling that in a neuromorphic sense? And then produce models that are perhaps better and stronger than what we can just do with deep learning. Then maybe that goes into a neuromorphic device. Maybe we go forward with that. But I think this is a much more interesting idea is to sort of broaden and expand this out. Now, with any move to a new technology, you end up having these technology drivers that drive us forward. So back in the 1880s, if you wanted to drive a car, you would get an electric car. There were about 30,000 electric cars back in 1880. I was astounded at that. I thought, seriously? There were 30,000 cars back in 1880? I don't think they even existed back then. And so they had the fastest cars in the world were electric. They had the market. The internal combustion engine was a very interesting idea. There were cars available, but it had two major problems. One is you had to crank the car to start it. Now, I have an old car, and I've gone out there with a torque wrench and turned the crankshaft. That's hard work. And you turn it, and it gives and then catches, and you can break your hand, arm. I mean, it's dicey. And the second thing is where do you get gas for your internal combustion engine? And so the two challenges were the starter and gas. And so once an electric starter was developed, and once a network of Standard Oil gas stations were developed, the internal combustion engine became very popular and more popular than the electric car. Oh, wait. So the next step was in the 90s, we started getting emissions controls, and people started saying, all right, we think there's too much pollution in the air. We think there's too many emissions from automobiles. Can we start to dial this back some? And then there was an emergence of electric cars. And the emergence of electric cars basically said, all right, I'm going to get a small car. I'm going to have a car that doesn't go very far. I'm going to have a car that's very expensive. And I'm going to have a car that's, maybe not the most attractive car on the road. And so no one wanted to buy it. It was uninteresting. And then we hit this paradigm shift, and we get this Tesla, where Tesla goes, wait a second, why don't we make it fast? Because electric cars can be really fast. Why don't we target a sports car market? And why don't we target early adopters, people who have a little bit of money and people who would be interested in a sports car? And so that'll then drive the rest of it. Now, I don't know where Tesla's going to go, but they certainly changed the view of how we look at electric cars, and most of the major car companies now are working towards electric cars that are more interesting. So does anybody own a Tesla? Yeah, all right. Yeah, good point. All right. So now if we look at the neuromorphic drivers. So we started off, we all know, ENIAC was the first, or arguably the first von Neumann architecture. Intel in the early 70s started the microprocessor revolution, incredible growth. Moore's Law, this engine that, every year we're getting faster, smaller processors, and it's just staggering what happened. And now we're at this sort of kind of end of Moore's Law. We're not quite sure what the future is going to bring. And we're starting to see more interest in things like neuromorphic and maybe quantum and some of the other areas. But the sense is going, what's next? What comes next? And so I think we're at this point right now of this kind of paradigm shift. We've worked in the field a lot. We have some great stuff we've done, very interesting research. But where do we go next? What's the next step we go? Do we continue in sort of a niche area, or do we start moving forward? And I think we need a neuromorphic Tesla. I think we need some big, clever ideas that say, all right, here's what this technology can be used for. Here's why it's significant. Here's why this could change the world. And that's kind of what I think we need. I'd love to be able to say, and now I'm going to tell you what that is in the next 5 slides. I'm not. I don't know what that is. But I think as a community working together and coming up with, a bunch of bright, clever people, this is something that we could come up with. And maybe the people who do could actually afford a Tesla. The main challenges I see, especially from the side of the world that I come from, is that machine learning, the stuff that we do tends to be driven by the current architecture. It's driven by a von Neumann architecture, and it's not particularly well suited for a neuromorphic approach. And then secondly, we have these data sets that we all use that are designed and driven by deep learning. And they're not necessarily well suited for a neuromorphic approach. People look at MNIST and you end up scanning the MNIST digit rather than just looking at the digit because you've got to make it fit with the architecture. And so I think what we need is we need to have neuromorphic learning, and we need to have neuromorphic data sets that we can test our learning algorithms against. And so my analogy is if I take a deep learning algorithm, I run it on a neuromorphic chip, and test it against a deep learning data set, it's like running my motorcycle, in a NASCAR race. You don't have a chance. You're putting your neuromorphic chip up against a GPU, and that's a very, very hard thing to win. However, I can't take one of those cars and put it on this trail. I think we've got areas that we do very well, that we're very well suited for, that we need to adjust to and need to focus on. So let me talk a little bit about machine learning. And this goes into a little bit of background, and I think you probably most know this. But machine learning, we started off with statistics, and it was pretty straightforward. You do an experiment, you generate data, you analyze the data to see, does my hypothesis work or doesn't it work? And you think of the classic rolling the dice experiment. Unsupervised learning, I don't know anything about the data. So you go into Kroger, you buy something, you give them your little card, they record everything you've bought, they take all that data back, and they start saying, if I group what people buy, I notice that people tend to buy beer and potato chips. So maybe I'll put my potato chips next to my beer and sell more of both. That's classic unsupervised learning. Supervised learning, the best in the world at it is Google. So you put in a search term, you then land at a page. So somebody says, I want to know about the Eiffel Tower. There are tens of thousands or millions of people that put in Eiffel Tower, and you have a ton of examples of where people go, what page they stop at. And that is classic supervised learning. Give me a label, I'll give you a page. And it works very well. And then lastly is this idea of more of a Facebook. So you go to Paris, you go to the Eiffel Tower, you get your picture. All right, you stand there with trying to get your, the Eiffel Tower in your fingers, and you take the picture. You post it on Facebook and say, we had a great time in Paris. Bob and Jim at the Eiffel Tower. There are thousands, tens of thousands, hundreds of thousands of those pictures. You can say, all right, I'm going to start training on those pictures so that when I see that, I go, oh, that's the Eiffel Tower. And I can say to you, or Facebook can say to you, is that the Eiffel Tower? And that gives you the ability to go, yes, that is, exactly. And so this is kind of where we're at on the machine learning side. Now, if you take a step down and look at some of these algorithms, there's some really common things. One is you end up having this really high number of comparisons. You end up taking data, it's typically in some kind of vector form, numbers, and then you start comparing numbers against numbers. The worst case is having to compare everything against everything. If you have to do that, it's going to take forever. So you look for tricks and ways to get around that. The next thing is you want to find very efficient representations. If my data is not stored well and it takes a long time to get through, that's not going to work out. You need to have very fast I/O, very fast memory, very fast disks. And then you need to have parallel information. So the bottom line is I have information that comes in here. I've got to crunch it through this thing as fast as possible, and then I've got to get it to an output device. So I've got to optimize the speed in, optimize the speed out, and try to get as many of these lined up as I possibly can. And that drives the algorithms we have. And that's very much of a von Neumann approach that says, here's how we deal with data. And so some of the characteristics of the data. This is a nightmare. This hairball, but this is a very common set of data. This is a typical kind of graph stuff. So I'm looking for data that's sparse. I want data that's clumped up in these very separate independent clumps that I can then put on separate processors. I can have that work away. I can get a result, come back and show an answer. If I get this, I've got to do that in a serial process, and it'll take forever, and I'm not going to get a very good answer. Graphs, if I have a graph, I've got to flatten it out so I can do some kind of locality. I need to know what's coming next. In a graph, I don't know what's coming next. All I know is I'm here. I could go a number of places. So I need to flatten it out and put it into some kind of table. I've got to do tricks. Most of the algorithms that deal with data are going to be non-polynomial algorithms. Some of them are very complicated, very hard to get a perfect, ideal result. So we do a lot of tricks, a lot of heuristics, a lot of transformations, a lot of feature reductions. I've got 35 columns. Can I get it down to 5? Is there a way to shrink it down to a smaller set? And then I adapt to the hardware. So basically, for learning by a machine, you end up going as hardware-driven, driven by the data characteristics. And I think about this comparison. So we all have seen this. We probably all have shown this. We probably all have a slide about it, comparing the brain to a von Neumann computer. And the computer, it's a great illustration, and it's stunning how different they are. So I'm thinking we need to kind of take that a step further and go to learning. Take a look at human learning versus the way a machine learns and start to say, are there analogies? Are there things we can pick up? Now, I know you can argue that a lot of these things can be it's kind of like reinforcement learning, or it's kind of like the flavor of learning you like. Maybe, but there's an awful lot of differences. We generate our information with sensors, with our ears, our eyes. That's how we gather information. We learn from pleasure and pain. You touch a stove once, you pretty much figure out that's a bad idea. Repetition, most people, if they learn something, they've got to hear it 5, 6, 7, 8 times. You tell a computer something once, it stores it forever. So it's how does that work? And then, one of my favorites is language. So I'm up here talking to you. You're hearing me. You're interpreting what I say. You look at most of the knowledge, most of the wisdom of the world can be read about in a book going back, thousands of years. So basically, the whole of human civilization, of knowledge, is stored in language, and it's a very powerful, very interesting thing. How do we capture that? How do we deal with that with a computer system? And then lastly, passion. I mean, you look at these kids. Some of these kids are like hanging on every word, like this is great, and then some of these other people are, checked out, do an email, Barney. So I think we ought to think about new ideas. And one for me, and I just threw down a couple of these, but one for me is to say, if I have this data that's represented as a graph, and it's a sort of a messy, ugly graph, and I've got a device that deals with graphs and naturally deals with graphs and can deal with graphs fairly quickly, well, that seems like it would be a very interesting and natural capability. From a data analytics side, if I had a device that could deal with graphs and work effectively with graphs, that would be huge. That would be an incredible capability to have. And so I think, it seems to me that we ought to have some, can we look at a graph representation learning method on a neuromorphic? I was talking with Katie the other day, and she was talking about, can we take a spiking neural network, train it against several different applications, and start to understand what are the characteristics to do general learning? What can you have that isn't specific to an application, but it's something that you've gleaned from several applications, a structure that says this is sort of an innate way to learn stuff. It's kind of a good way to put things together. And I think that's an interesting idea. I like that idea a lot. Temporal-based, with spiking approach is seemingly natural. But this, to me, is a great area for us to look at, is to say, what are these natural learning models? And I know many of you in here have thought about this and looked at this, but this is complicated. It's a very challenging thing to do because the architecture that we're dealing with is very different, very unusual compared to what most of us are used to. All right, now a little bit on data sets. So data's had this evolution and this enormous impact. So we, started with kind of experimentally driven in science. You think of the double slit experiment, gives some insight into how light works, into how, quantum mechanics works and how funky things get. Then you've got simulation driven was the next big phase, and that drove some of the large computing. If you want to do experiments on a star, that's kind of difficult, so you may have to do simulations. If you want to do experiments on climate, that's hard as well. So simulation gives you a sense of what could potentially happen, what are sort of the bounds of the problem. And then we're down to observation data. So I don't know if you can tell, that's a selfie stick. So I wanted to put a selfie picture on here. This is just a little bit of free advice here. I wanted to put a selfie picture on here. And so when you think selfie, who do you think of? I thought of Kim Kardashian. So I said, selfie Kim Kardashian. And I happened to do this query at work, Barney. I wouldn't recommend that. That's probably not a great thing. Yes, I know, we'll talk afterwards. But anyway, you've got this observation data, and basically it's free form, fairly raw. If you really think about it, it's kind of staggering. You look at Facebook and you look at Google, they're giving their service for free. How much infrastructure do they have? How many computers? How many people are running this infrastructure? How much profits do they make? And you go, this is an incredible amount of money that's being generated and produced and that from data that we're providing. And so it really sort of amps up from the, yes, this is a nice esoteric little experiment, to this data can be monetized in ways that are just staggering. Anyway, so, from the data that we typically look at from this observed data, it's going to be large, high-dimensional, non-numeric. What used to be experiments, you write down numbers, you put it in a table. Most of the data that we look at is non-numeric, and it's got to be somehow translated or shifted. We have a lot of these curated data sets that we use. I would be willing to bet we're going to see MNIST a couple times this week. I've used MNIST. I mean, it's one of those, it's a great data set. It's easy to use, easy to pick up. And then people, the classic is you have researchers saying, I want to test my algorithm against the community. I want to see, how does my algorithm work? How do I perform? And so I think we ought to look at having data sets that are geared for a neuromorphic computing. Rather than looking at the deep learning data sets, develop some new ones on our own. I would suspect the data would be highly connected, probably time series, maybe multimodal. But I think this would be a great thing for this community to be looking at and saying, what do we do with this? You see, what I'd like to see of the next steps is to say, can we develop our own benchmarks? I would love for ICONS 2019 to say we have a data challenge. Here's a data set. I'd love to figure out what the metrics are. Maybe it's power, maybe it's accuracy, maybe it's connectivity of the data. I don't know. But it would be wonderful to have that and have somebody to put this together, somebody to curate it. I'd love to have these data challenges and prizes. It's kind of fun to say, all right, you got a couple researchers across the world that are saying, what's the I got this, how about you? And you sort of have the friendly competition. So in the high-performance computing world, there's this prize called the Gordon Bell Award, or Gordon Bell Prize. And it started off, many years ago, somebody bet another researcher that he couldn't get the results that the guy was promising. And it started off as this sort of, funny competition. And then it came to the point of being the main prize in high-performance computing. It's this huge prize. So I'm thinking we need like a Robinson Pino Prize that we can have to kind of say, here's how you judge the the value of your neuromorphic system, and then we can publish results against it, and we can have our own stuff. Now, the last thing I want to talk a little bit about is programs. So we've about 5 years ago in the deep learning area, there was a guy named Andrew Ng, and he had 64 nodes, GPU nodes, that he put together in this cluster, and he did something with cats. He did some kind of way of automatically recognizing cats, and there was a big splash about it. And one of the people in my group said, well, 64 nodes, 64 GPUs is interesting, but, across the hall, we've got 18,000 GPUs. Maybe we could do something. And I thought, I'm not so sure, but maybe we can give it a shot. And so we came up with this idea of saying, let's use this big computer, let's use evolutionary optimization to be able to generate these deep learning networks. And so it was a great idea. We wrote a paper on it. We submitted it to our internal funding people. And they, of course, said, son, this didn't work in the 80s. Why do you think it's going to work now? And so we kind of went back to the drawing board. We started socializing the idea. There was a 2-day hackathon. And so 2 days, and we're running not on Titan, but on kind of a Titan sandbox. You have to kind of prove yourself on the sandbox before you can actually play with the real computer. And so we had this 2-day thing. We had this result that looked very promising. Actually, Robinson was there and Mike Berry, and I think I actually took this picture, but I wouldn't guarantee that. But it was just this fun couple-day thing, and we were all excited about it. And so then we said, all right, let's go in and try again a year later to get internal funding. So we got some internal funding. We got a little bit of time on Titan, and we started moving forward. So we ran on 10 nodes, and we got great results. I mean, great results. We ran on 100 nodes, and we got good results. I mean, they were pretty good. We've scaled up to 1,000 nodes. They were horrible. It was terrible. The thing didn't scale. And so we're at the point of going, all right, we're getting towards the end of this funding. We've used up most of our time. What are we going to do? And so we ended up going through and coming up with this clever idea about doing asynchronous global optimization using evolutionary optimization. And we finally got it to work and got it to run on all of Titan and good results. We sat down and said, all right, where do we want to go with this? What's our future? What's the 2 years from now? What do we want to be able to say? And this was a really valuable exercise. We said, well, we want to get some funding from DOE. We want to get an ALCC award, a bunch of computer time. We want to get a Gordon Bell Award. I mean, seriously, a Gordon Bell Award? We don't even know how to spell Gordon Bell. And so then we are 2 years later. So we got funding from DOE. We got this Mendel project running on all of Titan Summit, a bunch of collaborations. And we just heard we're Gordon Bell finalists, which I'm really proud of, but we are so far out in left field to be considered for this. It's funny, but it's not. But this is our next step. Just to say, all right, we have some, Katie's got this EONS work she's doing. How can we start to merge that in? Maybe with some of the deep learning work, start saying, how do we get that running on big computers? How do we start going forward with new ideas and hopefully this, a broader, more expansive view of neuromorphic computing? And so anyway, my idea for the, sort of the program is, the initial things that you need are going to be a national, cause for it. I mean, why would you spend public money to do these kind of things? Well, we had a report that we did 2 years ago in the 2016 workshop that lays that out. It was great seeing Intel here. I mean, it seems like they've got a very interesting chip. It seems like there's a market there. It seems like it's progressing forward. I think we need a paradigm shift. I think we need to sort of move away from some of the feasibility approaches and start saying, how do we use these things natively? What are the algorithms? What are the data that we that we go forward with? I would love to get standardized data sets. As far as the funding goes, I know a lot of people from DOE and DOD are working hard to make this happen, and I'm pretty optimistic that will happen. And I think we need this Tesla idea. Big, clever, creative idea, something kind of out of the box, some way of looking at neuromorphic in a way that most of us kind of wouldn't look at and maybe go, that won't work. But kind of those new big ideas. And I also want to highlight the collaboration. We have several sort of stovepipes or what do they call them, spheres of excellence in the community. And I think it would be great to say, can we work together in a broader sense? Can we get the device people and the system people and the algorithm people and the data people to work together and start to jointly come up with some of these things? And so this is it. So basically for me, I think the future is bright. I think we're in a great area. I think neuromorphic computing has a tremendous future, and I think this is a wonderful area to be in now, and I think it's got a great future. We need all of you, big, clever, creative ideas, things that are outside of the box, open collaborations, learning, and data sets. So anyway, welcome to ICONS. I hope you have a great conference. I think we've got a great lineup this year. I'd be happy to answer any questions, comments.
Any questions for Tom?
Just one comment, Tom. I agree with all of this, but when you're talking about new benchmarks for neuromorphic computing, one of the challenges and one of the things I think we need to think about is that we target things like control applications, like navigation, equilibrium, targeting, things that are hard to quantify with the data set because the data set's static, whereas the application that we're targeting is not static. It's going to be affected by the device. So I'd like to include that in the challenge of what we do is to somehow get the framework, because it's really hard to express a control problem as a benchmark. But we need to do that because I think that's a real opportunity in our space.
Yeah, I agree fully. As a data guy, it's hard for me to kind of do the application side, but I agree. I think that's a great point. Yeah, Mark. There you go.
The other thing, I agree with Jim, the other thing I would suggest we put on the challenge list is, especially for DoD, is both approach to verification, because unlike traditional computing, we don't necessarily have a quantifiable way to verify that the network's going to operate as expected. And the other thing that I've got a lot of feedback from is safety. How do we verify that this neuromorphic computing, this neural network, won't run awry and do something unexpected? So some safeguards maybe in the design of the network would be good to have as well.
Yeah, that's a great point.
I was interested in your talk about, I guess, human aspect of learning and integrating that in with neuromorphic and stuff. I was interested in your thoughts on sort of the balance between going so far and mimicking human brain versus, trying to stick more computationally, and where we might run into just arbitrarily including things that are sort of superfluous in the effort to try and, head towards human-like learning.
Right. No, I think that's a good point. I think we've seen that on the neuromorphic side, where you can get to the point of being biologically correct, but having such a complex device that it really isn't very usable. I think with looking at human learning, I think you'd run into the same thing. I mean, ultimately, you end up talking to psychologists and people that go, here's how humans learn, here's how we think the brain works, but none of it's clear. So to me, I go, I think the machine learning approaches we've taken tend to be very mathematical and very statistical, and we really haven't thought much about, well, how does a human learn? And so I think it's, to me, if we can make a little bit of a step, maybe there's some insights that we can gain from it. As far as trying to really mimic human learning, I don't think we understand it well enough to do too much.
So my question relates very much to that. I guess, how does this community, in your opinion, and you talk about collaboration, we can bring together the neuromorphic community, and I think that's starting to happen. But how do we bring in the relevant cognitive scientists, neuroscientists, these existing fields that need to probably be part of that conversation, because they were there in the 50s when neural nets originally came up. So how do we get those communities back into this room, from your opinion?
Well, I think that's a great point. Maybe it's through conferences. Maybe it's through NICE and ICONs. Maybe we end up saying other ways to, we tried, I think last year, 2 years ago, a keynote speech with it was more of on the neuroscience side. But I think that's valuable. I think it'd be very helpful. There's a bit of a challenge of just getting the language right, so that you can sort of have some meaningful communication. And but I think that's essential. Maybe it's projects. Maybe we have, if we can define projects that can bridge the gaps, that could be valuable as well. But it's a great point.
Yeah, I have a question here. Like anytime I bring this neuromorphic computing in meetings or conferences, the question I always get back is like, it seems kind of more target thing, like you do computing, but always like in their mind, like when you use it for application, you still want to use like a typical processor to do other thing, like the memory, the display, and that stuff, So how you see that? I mean, like, is it really true? Like this neuromorphic computing is just about computing. There's no way in the future that we can do more than this, like. To me, that's a bigger challenge. People, they stick with the typical computer and what can do for them. And for them, it's hard to imagine, like, in a way, and in the future, that neuromorphic computing can do all that for them.
Yeah. If I had to guess, and this is really a guess, you look at GPUs, where GPUs become an accelerator for CPUs, and that then enables something like a deep learning. If you don't have that capability, you can't do it. And I would suspect at first you end up going, can you take a neuromorphic chip as some kind of accelerator or some kind of capability that you don't have on it with a conventional computer? It's like the graph stuff to me is interesting. If there was a way you could do something interesting with a graph structure on a neuromorphic chip on a conventional computer, that could be a very, very interesting idea, interesting approach. I would see it that way. I don't know if I quite see a neuromorphic as being a replacement for what we have now, but I think it can certainly enhance and add to what our capabilities are.
A follow-up comment on the previous question from over there. I'm from Europe, so maybe I can bring something about how we work with the neuroscientists, and that's happening in Europe. I've been working in the neuromorphic engineering field since almost 20 years now, and one way to do it is collaboration, so the last thing that you propose. There are also meetings where these kind of things are happening, so one of it is in the States, so the Telluride Neuromorphic Workshop, where Terry Senioski, a computational neuroscientist, has been bringing people there, and there's a tight relation between the two communities. So I think these things have been there, at least in Europe. I've experienced them the whole time. If you feel like here, I'm new to this conference, so if you feel like here you're missing this side of things, I think it's possible, and I think we have a very good experience with that in Europe.
Well, I'm glad you're here, and I would love to have that. I would love to have that collaboration. I think that would be really wonderful.
Yeah. So regarding the problem of benchmark tasks and the issues of time and control systems being things of interest, as you'll see in the next talk, our take on it for benchmark tasks goes something like this. The task is to predict what the input is, but also to act upon that input in order to be able to improve prediction. And you'll see that in the context of a visual model, but I think that could be a paradigm that we could expand upon.
Mm-hmm. That's great. All right, thank you very much.